You set the code protection bits on your microcontroller. Does it actually do what you think it's doing? We're going to take a survey at 3 different microcontrollers, explore a variety of attacks, and discover the times when code protection doesn't protect code. I'm Crandyman, and welcome to the debut of Assembly Tech Security. Just as a quick intro, Assembly Tech Security specializes in vulnerability research, reverse engineering, and cybersecurity education. You may have seen us at a few different B-sides around the Central Florida area, and I was recently at HackSpaceCon. This is going to be a recording of the talk that I gave there, rehashed, and it's going to be full form, just like I gave it at the conference. It's going to be pretty raw, pretty straightforward, but we're glad to have you here, and let's look at the times when code protection doesn't protect code. All right, so first of all, we're going to look at what is code protection. We're going to talk about what it is, what it isn't. We're going to look at some attack categories, and then we're going to look at 3 examples: the RP2350, the MSP430, the PIC18F-XX2, and have a few different parting thoughts. I'm not the original discoverer of these attacks. I may use the royal we throughout, but a lot of credit and a lot of great work has been done by other researchers, and the sources are slided at the end of the slides. So about me, I'm the lead instructor at Assembly Tech Security. I've done 12 years in vulnerability research, reverse engineering, government contracting, and big tech. Did some public bypasses, done some education, and a few different things in the CTF scene, including ShmooCon, various B-sides, and other events. But really, we're here to talk about code protection. So what do we mean when we talk about code protection? The primary thing that we're talking about is flash protection. These microcontrollers have memory embedded inside of them, and the goal of the flash protection is to prevent peripherals like UART, JTAG, or some vendor-provided tools from reading the embedded flash via the external pins. It may include similar protections for data sections or boot ROM or any other different internal flash banks, and it can also have vendor-specific terms like code readout protection. The motivation of this is really security through obscurity, where we're trying to prevent against unauthorized access of the firmware, the code that's running on the microcontroller. It may also include any secret keys or other proprietary information in the microcontroller. There's also secure boot. Now, secure boot is different than code protection, but many of the attacks against it can also target code protection, and so we're going to look at a few different attacks against these implementations. And really what this is a firmware security feature that uses cryptographic algorithms to verify that you're running trusted code. A lot of times, really most of the time, the cryptographic algorithms and the secure boot software itself are readily accessible and inspectable. And the thing that's kept secret is just the private key value that's used for that asymmetric encryption. The key purpose here is that it ensures the bootloader only loads approved digitally signed software. And this fits into Kirchhoff's principles that a truly secure system should remain secure even if everyone knows everything about it other than that secret key. And so this provides security through transparency. And why do you care? From a defensive perspective, you want to make sure that you're picking the right microcontrollers to protect your assets and properly utilizing their security features. You want to make sure you actually are enabling code protection that you expected. From an offensive perspective, it is hard to find and exploit vulnerabilities without a binary and without code to look at. From a business perspective, you want to better understand the adversarial threats, including where to put your investments to meaningfully increase the cost and difficulty for attackers to obtain your business assets. And from a philosophical perspective, to paraphrase Isaac Asimov, any code worth protecting is code worth reading, just like any book worth banning is a book worth reading. And even things that you think shouldn't fall into adversarial hands at some point probably will, somewhere, somehow. Now, it's okay if you don't understand all the technical details. The point of this presentation is to show the art of what's possible, what attacks are being done, and understand how attackers look at inspecting these microcontroller targets. So, looking at these attack categories, we're going to break down some techniques. And glitching is really the relatively new hotness. As an attack vector, it's been around for quite a while, but the educational resources around it, more accessible open source hardware and tooling, commercially available resources, they've really grown in popularity within the last handful of years. What we're doing is we're attacking physics to change the behavior of the MCU. We're doing things like dropping the voltage briefly. We're trying to inject an extra rising edge into the clock signal. We're using electromagnetic fault injection and RF emissions. We're using lasers and ultraviolet light in an attempt to induce photovoltaic effects. You can use temperature, hot or cold, to try to make the silicon behave in an unexpected way. Now, usually this has really tight timing requirements and location requirements. By timing, meaning we are targeting the glitch against a single specific instruction during the execution of the firmware. And that is really tight timing, especially at some higher clock speeds. And when I mean location, when we're looking at electromagnetic fault injection specifically, that tool needs to be precise coordinates on the chip, X, Y, and Z axes. And you also need to make sure that you're targeting the correct power rail when you're doing voltage glitching. So you want to make sure you're trying to glitch the right thing with the right technique for the task. Now, when we look at glitching, there are a few different effects that we're trying to achieve. By definition, we're introducing some undefined behavior, but there are some potential outcomes that we see repeatedly when glitches are successful. The most common one we see is skipping an instruction, where an instruction just doesn't actually execute all the way, or doesn't execute at all. We also have malformed data reads and data writes, or maybe we decode the instruction incorrectly and we're not executing the instruction that was programmed. This image here looks at what a voltage glitch looks like on an oscilloscope, where we have stable voltage and then briefly drop it just long enough to induce some weird behavior. Physical inspection is literally seeing ones and zeros with high-res photos. This is really cool, and this image is using a metallurgical microscope at only 50 times zoom to look at Game Boy ROM. And you can use X-rays. There are a few different technologies and resources available to use different imaging technologies to look at the silicon. And scanning electron microscopes and focused ion beams are some of the more cutting edge ways to do this. If you have the money, you can of course stand up your own lab, have your own expensive ion beam machine, but you can also rent one. And there's some going rates at the University of Washington as of about March 2026, and even help that you can get by renting some staff to help you work the machine. Side channels are not really an attack per se, but they're a class of vulnerabilities that attack how the code executes without seeing what data it's operating on. What we're really talking about is that we're passively monitoring traits like timing, how long code takes to execute. We're looking at power consumption, temperature, RF emission that happens, and we're looking at how the chip is behaving in order to get information about what data it's operating on. Some techniques are more active than others. For example, in the Spectre situation, trying to groom a speculative branch predictor, but the things we're going to be looking at are primarily passive today. Now, glitching and all this is awesome, but usually requires a little more time, money, and or luck. Of course, you can create your own luck in this world and get really good at some of these glitching attacks, but there are logic flaws and misconfigurations that don't require extra equipment and don't require that sensitive of timing. When we look at the effects that we can have, a flawed flash protection or secure boot implementation can make all microcontrollers vulnerable, by which I mean if one microcontroller has a flawed implementation, any product, any vendor that uses that could be affected. Whereas we can also see logic flaws in how people configure chips, and that can make individual vendor product lines vulnerable. Think, for example, of someone who makes a single product and they misconfigured the chip, it really just affects that product line. And these logic flaws are cheaper, more deterministic, but again, because they're configuration dependent, they also tend to be product dependent. For example, we're going to start going and looking at the Raspberry Pi 2350. So about this, it's a really cool chip. It's low cost and has both ARM cores and RISC-V cores. And you can choose which ones you're executing as part of the configuration bits. The key thing that we're going to look at here is the one-time programmable flash, or the OTP, that's used to store secrets among some other important configuration data. It includes some awesome technology like secure boot and has some mitigations that we'll discuss. Interestingly, it's not for safety critical applications and is released just a couple of years ago in 2024. And its release story is actually pretty interesting. So they introduced it at DEF CON with a $10,000 challenge to hack it. And then 30 days later, with no successful submissions, the prize doubled and the contest was extended. So we're going to look at 5 valid approaches that all succeeded in their attacks. And this is really cool, and it really shows that even with a huge security focus in your project, it's still vulnerable and things still happen. By hack it, I also mean the goal was trying to read out a 16-byte value from the embedded flash. And that flash was marked as non-readable in OTP, and secure boot was enabled. So before going into the attacks, we're also going to talk about some of the mitigations that the RP2350 implements. And the first one is a glitch detector. So the general concept is that there's circuitry that will take each clock signal, and these 2 different flip-flops here will both take the clock input, the rising and falling edges of the clock, as input, and then output that through a flip-flop. But one of those has a delay. And during normal operation, that delay doesn't make any significant difference. The output of those two flip-flops should always match. But if they ever mismatch, someone's probably attempting to glitch. There's another couple interesting things that this is within the core voltage domain, and that the propagation delay is configurable and is as a fraction of the maximum system clock, rather than a fixed time in nanoseconds. So this is a really important piece of circuitry and seems to prevent any type of glitches from happening. Additionally, there's a redundancy coprocessor, and really it's used to provide hardware-assisted mitigations against fault injections. Generally used to create random values, introduce random delays, and enforce in-order execution. As a coprocessor, it has its own interface that is invoked via assembly. There are also guard reads. So these happen by detecting if glitching is happening by trying to read a specific field in memory that has an expected bit pattern. For example, all 3s or all Cs. And the goal is that if the guard read matches the expected value, then we're clear and good to try reading the guarded memory region. But if for some reason that guard read doesn't match, then we'd rather fail predictably than proceed in an inconsistent state. So this tries to protect glitching and trying to prevent improper memory reads. So looking at the first approach, we're going to look at the OTP and we're going to look at double glitching. So even when the OTP is configured to be non-readable, when the bootloader is starting the processor, it still needs to read that OTP memory because it contains critical chip configuration information in the CRIT1 register. And so the bootloader needs to read it and then afterwards lock it down into the correct configuration. So even when the OTP is supposed to be inaccessible, the early bootloader still has to read it. So our goal here is, can we glitch the bootloader to prevent that OTP lockdown? And then after preventing that lockdown, when we get to our code, hopefully we can read it out via USB or UART. And we're going to look at the target code here. So this code has a few functions that are interesting, and that's that SOTP advanced BL to S value, kind of log name. But as we look at what's happening, its security is so important as they're looking at this operation and looking at the values of this configuration register, they actually read it twice and then assert or check that the value is the exact same. So could we just like glitch it twice? And if we glitch it twice, will it have the exact same value each time? It sounds kind of like an impossible task, but let's look at what's inside that function. Inside there is a logical shift left and right pair. So if you think of your bitwise operations, we are shifting the values of the configuration register left and then shifting it back right in order to clear out the upper 28 bits. But this proposes an interesting scenario. If we can shift it left, but then glitch and skip the shift back to the right, that means we've left the lower OTP bits cleared. They were cleared as part of that shift left. And an OTP page can then remain read right instead of the expected inaccessible. Because as you look through here through this loop, we're going through a loop, and for every page in the OTP, we're checking the configurations of that page. And so we can have it execute the shift left as expected, glitch, and skip the shift back right, and that leaves it in the read write state. But inside that function are two of these random redundancy coprocessor random delays. So how do we know when to glitch? Well, it turns out when you do random delays, idling delays does very little power consumption. So when we look at the power trace, this is one of the side channels we're talking about. We can look at the power usage of the chip and see these low power consumption times as an indicator that we are in one of those RCP delays. And using these drops in power as a trigger for your glitch, and then you can reliably do that. And reliability is a strong word. It still has a random delay, but you just aim for the middle of the window. And as an attacker, you only have to get lucky once, and the attackers did. They were able to extract the contents of OTP memory. So what about the mitigations that we're supposed to prevent against this? When we look at the glitch detector circuitry, note that it was on the core voltage power rail. And what this attack didn't use voltage glitching. It used EMFI, specifically the chip shouter, to induce a fault in the post-detector circuitry. So if you look at the image there, we have the EMFI or chip shouter tool above the RP2350, and there's a little coil right above that chip that will burst RF energy. And it induces this fault and affects the circuitry after the glitch detector has already happened. Additionally, we saw how the RCP randomized delays could be used as a trigger signal to actually help us find our timing when to do it correctly. And even though the code specifically tried to prevent us from reading it, and it would do a double read and a compare to try to make sure it was correct, we still got lucky. We only have to get lucky once, and glitching it twice is a feasible attack. So attack number 2 is attacking the OTP power rail. So we've already talked about how OTP contained important configuration information in the crit1 field. Some of the things that it configures are the debug access, core selection, whether you're using ARM or RISC-V, glitch detectors, a secure boot, all those different configurations. The OTP itself has a dedicated power rail that comes from an external pin. And there's a power on state machine that's used to manage system resets and power states. Like many microcontrollers, there are several different power rails, but a lot of times they will draw from a common power source on the board. So you only have one battery or one input power source that's used to be shared across different rails. Our goal is to isolate the OTP power rail from the shared power source and use that as a dedicated attack to try to glitch the power on state machine. And this is going to make a lot more sense with some pictures. So as we look at the OTP, this antifuse array, that is where the actual data, the secret data, is being stored. Those are the ones and zeros that we're trying to get. But as we look over at the OTP, there's also an integrated power supply, the IPS. And if we look a little bit closer, we can overlay and see some internal pads. And there's these pads right here that are above the OTP IPS and also right next to the USB interface. And if we zoom out a little bit more, we can see that there are bonding wires that actually take those two internal pads and attach them to a single pin external to the chip. And this is labeled in the datasheet as the USB OTP voltage rail, VDD. So it's accurately labeled and it's pretty clear to show us that it's being used to power the USB as well as the OTP. And this comes from the datasheet. The RP2350 is very open and has a great data sheet that's available to read. So as we look at this, these rails, and looking here to the side as well, we see the QSPI IOVD. There's another power rail right next to it. And they are actually on top of a shared copper pad. And that's what we're talking about when we say that a single power source can be used to power multiple rails. So what we actually do is lift this chip up, cut the pad underneath to isolate it, and separate the USB OTP power rail from the QSPI power rail. And this is an image of how they did that. And this way now we can have a direct avenue to try to target the OTP voltage power rail without interfering or causing effects on any of the other pins that share that power source. So we're going to skip over the specifics of the glitch because it's fairly similar to the other one, but it turns out that when we can glitch this power rail, one of the things that we get is several bits set in the OTP critical register. You'll notice those bits set up there. We have 0003, 0033, that's the value, and we have some of the important bits highlighted in blue. Note that this kind of garbage value that gets left in the configuration bits says that both RISC-V and ARM are disabled. And this is conflicting, and it just so happens that in this scenario, it will end up selecting the RISC-V cores, and then the debug disable bit says that we can enable RISC-V debugging. That bit is clear, so we have selected the RISC-V cores and enabled RISC-V debugging. This is also very interesting because for this challenge, the secure configuration meant that the RISC-V cores were permanently disabled. And instead, because of the way this glitch happens, we're actually able to re-enable those cores. And now we have the RISC-V cores, which provides full memory bus access, and we can attach a JTAG debugger to that to read the secret out of OTP memory. So what about the mitigations that were supposed to prevent this? Well, the glitch detector, you'll notice it said it was on the core voltage power rail, not on the USB OTP. So we actually have two separate power rails used, and we try to target this other one that doesn't have the glitch detector circuitry in it. The guard reads that were supposed to protect and prevent against this had a value of all threes. And it turns out that's where we see some of these threes come from, is because the guard read was supposed to be all threes, and some of those got latched and propagated as the values read from memory because of the timing of this glitch. And that's what allows us to set all those different bits that allow full RISC-V debugging. We'd also look at the redundancy coprocessor and try to think of mitigations it could do to prevent against this. But the interesting thing here is that this is so early in the bootloader that we're able to exploit it before the RCP itself is even booted. All right, we've already talked about the power on state machine, but now we're going to talk about a different part of it. There's a part of the PSM that manages reboots. And like most microcontrollers, the way it handles reboots is different from how it handles cold boots. There's a reboot option with the name reboot type PCSP, which you may recognize as program counter and stack pointer. And this essentially allows executing from an arbitrary program counter and stack location. You can tell this is very sensitive and could be a security issue, and so this reboot option is only allowed from the secure world, which on ARM, these ARM cores, is trust zone. But when rebooting via the normal world USB, the assembly that handles this actually looks like this. And if you look at the green text, you'll see a conditional branch non-zero. And if we're able to skip that instruction, the thing that we fall through is the label for handling the PCSP reboot type. So this actually gives us a pretty compelling glitch target. If we can glitch and skip that conditional branch, we can fall through and go to the PCSP reboot vector that we shouldn't be able to access. And this is possible. Research has demonstrated the glitches in the presence of glitch detectors. So as we look at the glitch detectors, remember how the datasheet mentioned the detectors could be run as a fraction of the maximum system clock. Well, it turns out when you're in this USB bootloader mode, it actually uses a much slower clock than normal execution. It's part of the USB timing. And because it slows that clock down, that actually gives us a wider glitching window. And so the glitch detector may not really detect such a rapid pulse because it's now a smaller glitch in the larger window that we have due to the lower clock speed. Now note the winner didn't actually get this specific glitch to happen successfully at this specific spot, but they were able to demonstrate it in the presence of the glitch detectors elsewhere, and the Raspberry Pi Foundation said the theory was sound enough and it did count as a valid submission. Now we're going to move away from some of the voltage and EMFI glitching and actually look at laser faults. So this is a little more nebulous goal up front where we want to do an exploratory search to see what behavior we can induce without triggering the glitch detectors. The intent is to convert energy from the laser into electrical energy and voltage in the circuitry, which is called the photovoltaic effect. The goal and way to do this is to mechanically expose the underside of the microcontroller, whether that's through abrasion or a chemical, some way we're going to clear and expose the underside of the microcontroller. And then we put that on top of a custom PCB board that has a hole underneath the chip that we can shine our laser up through. At that point, we can then slowly scan across the die and experiment with parameters like power, focus, other light amplification parameters. And if we reach a point where the ARM core execution flow seems to be disturbed, but we haven't triggered the glitch detectors, we think we found an interesting area. And once we find that interesting XY coordinate on the microcontroller, then we can experiment with timing to influence how the effects manifest themselves and how different instructions behave. So this is a really cool setup and is particularly awesome because the original author provides schematics, part numbers, and everything for this homebrew laser setup. That includes the positioning system, the laser diode, other supporting materials, and they say it's an order of magnitude cheaper than a professional setup. So if we look right here, we can see that this is our PCB board with the RP2350 on top. There's a hole underneath the chip in that PCB, and there we see the laser shining up underneath it. Now that laser is controlled X and XY axes with these two servos, and that's controlled by that board. And then there's this I/O input-output board attached to it through the ribbon cable. Because as we look at this, here's the code that we're trying to target. We are trying to target this code that is checking the hash as part of the secure boot process. And we're not actually doing a pass the hash attack, just talking about this hashing code here. What we're looking at is the highlighted instruction, the move S R1R4. Prior to this point in the code that we're trying to execute has been copied out of the ROM into RAM, which is where it's going to be executing out of. So we have a legitimate piece of firmware that we're copying out of ROM into the RAM where it will actually be executed. But you'll notice that we can glitch this highlighted instruction, which prevents the source buffer from getting reassigned. This means that this move into R1 doesn't actually happen. And if it doesn't happen, that means the stale value that's there in R1 can point to either RAM or ROM flash. That's the attacker's choice. What this means is that we can, on cue, depending on when we do this timing attack, we can choose whether to compute the SHA-256 against the valid ROM in flash or the copy that resides in RAM, which could be an attacker version. And so because there's this mismatch, and because the way we can glitch it to choose one bank or the other, the ROM or the RAM, we can execute attacker code while satisfying the hash check that's been validated against the ROM copy of the code. And that's why there's that additional IO PCB board. It has two different flash banks, one of which contains malicious firmware, and the other one, the legitimate one, that will have a valid hash. Now, this is just one of the glitches that bypass the hash check. There were multiple other timings that glitched other instructions and caused similar issues, but they needed to be exploited differently. So as we look at the mitigations that would protect against this, the glitch detector only defends against voltage glitching that's coming in on the pin. And similar to the EMFI issue, if you have a laser that's inducing a fault after the glitch detector circuitry, then that's not able to be detected by the glitch detectors. And with approach number 5, this is our focused ion beam and trying to extract information from the antifuses. So if you remember the images we looked at, there was the OTP antifuse array. And I said those are the ones and zeros that held the secret data that we are looking at. And what we can do is use a focused ion beam to use positively charged ions to scan that and make an image of the antifuse memory and optically recover the individual bits of the secret that's stored in the OTP flash. And if you're familiar with fuses, antifuse is exactly the same, just inverted. It actually starts as a broken circuit, but then is programmed with voltage to make a short circuit and uses that to store non-volatile data. The way this happens and works is because physics, and essentially as we look at the focused ion beams, you want to use some low power beams to avoid damage and reduce sputtering. Sputtering is what happens when atoms from the sample get ejected from the sample surface because the focused ion beam introduces so much energy into it, it can actually dislodge atoms from the surface. So you want to be careful about your power beam consumption there. And just like we exposed the underside of the die when we did the laser fault injection, in this case, we're going to decap or delayer the layers down to the contact layer across the antifuse area. The rest of the microcontroller can be discarded. It doesn't need to be a functional chip. We just need to get down to the layer of the antifuse array, and then can use passive voltage contrast, or PVC. And I am not enough of a physicist to explain this in great detail, but the outcome is that we're able to recover the bitwise OR of two physically adjacent memory cells that share a common metal 1 contact. And ultimately, a picture is where it's at here, because this is credit to IO Active, how they're able to optically recover the contents of the antifuse array. You'll notice there's a calibration row, which has information or data that they know and helps them locate where they are in the antifuse array and in the OTP memory. And as you look at the shared metal 1 contacts, adjacent cells are actually able to get bright lights and dim lights to be the zeros and ones. And they have a great white paper they've done about that. And as far as a mitigations perspective, it's all irrelevant if you can see the woman in the red dress. This attack is the only one of the ones that we've talked about thus far that was not fixed, and honestly isn't really fixable. If you can get to the point where you can look at a chip and see the data in there, there's not really many mitigations that are going to protect you. You're going to need to invest in more physical anti-tamper and other solutions. So we've explored 5 different approaches, and is there a way that maybe we can generalize this approach and generalize this attack to find these issues on our own? And there is. If we look at it, I think of it as fault injection emulation. And credit to Stack Smashing and NSR, they gave a great talk where they were talking about their approach and their attacks here. But if we look at it at this step, there's 4 steps we can do here, where 1, we define a target condition. For example, at this point in the code, I want OTP memory to be readable. For example, by the time we get out of secure boot and are executing my user code, I want OTP memory to be readable. Then you want to characterize what you expect a successful fault injection to achieve. For example, we may assume that if I have a successful glitch, it's going to cause an instruction to be skipped. Then if you can emulate the bootloader, you can fuzz fault injections in software. Essentially, if we think that our glitch will cause an instruction to be skipped, then we can pick an instruction at random to skip during our emulation. Or you could do it sequentially and try to walk through the firmware and try to find an instruction at random to skip and see what happens. So if you can finish your emulation and get to your target point, and if you ever achieve the target condition, then it's a candidate to attempt on hardware. So we're doing it through emulation in software and using the structured approach to emulate or simulate these fault injection attacks, and then that should help us narrow in our focus when we want to do an actual hardware attack, which I think is a really cool and really scalable approach. All right, so we've gone through a lot with the RP2350. Bear with me here. We're going to go back in time and now look at the MSP430. So whereas the RP2350, very recent, very modern, MSP430 is a bit further back. We're going back to the 90s. And you probably have heard of this chip, whether you know it or not. It comes from Texas Instruments. And its key characteristics are that it really prioritized low power consumption and low cost, and was really popular for harsh environment applications. For example, Planetary Resources is a company that said that the MSP430 microcontroller is a key element of our spacecraft avionics architecture. Its extremely low power requirements make it very well suited to the spacecraft environment. There's over 570 variants of this MSP430 with different types of peripherals, different sizes of memory, but it's been used in a variety of interesting areas and industries, including automotive, military space, renewable energy, other things. As we look at how this is implemented, what they have is something called the bootstrap loader, or the BSL. And this is stored in mask ROM, which is permanent, unmodifiable, literally photolithographically written onto the chip. If you want to execute or go into the bootstrap loader, you just need to enter a specific pattern on the test and reset pins to enter BSL mode. And the BSL will remain functional even if JTAG is disabled via blown fuses. So this bootstrap loader is always around, and it's password protected. If you don't know the password, there's not too much that you can do other than wipe the chip. But if you do know the password, then you can read and write memory, and you can extract firmware and otherwise get full access to the chip. So as we look at this, what is this password and how strong is it? We know people who use, password 123 and other weak passwords, but as you look at the BSL, it's not something that the end user actually even gets to pick. It is the literal contents of the interrupt vector table. So we're actually taking 16 different 16-bit pointer values and concatenating them together for a total of 256 bits. But if you're familiar with your pointers, you'll probably realize that pointers aren't really good sources of random data. Only about 40 of those 256 bits are actually random. And so this introduces some optimizations. We can actually look at the bootstrap loader, and it turned out that increasing the baud rate was previously accessible in the BSL, even if you didn't know the password. And it was interesting because this actually changed the system clock speed, not just the UART baud rate. And so without knowing the password, you could increase the system clock speed, and now it's running at a faster baud rate to allow for faster guessing. But even so, brute forcing was not feasible. It still was on the order of decades to be able to execute this attack successfully. Remember, these are very low power, very low speed chips. So can we improve? Can we make this better? And we can, because there's an interesting way that this is implemented. As you look at how they're evaluating the password for correctness, there's a loop. For each byte in the password, it's going to check if it's the correct value. If it's not correct, then it's going to set a bit in R11, and we see that with the BIS instruction. And it goes through the entire password, and at the end, the program will check that bit in R11 to see if every byte in the password was correct or not. And this actually shows a pretty good probable intent. So a common side channel attack that other people might do is iterating through the password and saying, is the first byte correct? And if it's not, exit the loop. If it is correct, go to the second byte. Is the second byte correct? If not, exit the loop. And that exposes a fairly significant side channel for timing. So to avoid that, we don't exit the loop early. All we do is set a bit. So we're always going to run through the entire length of the password and make sure that we don't introduce that side channel attack for timing. But this introduces a new side channel. Every time we have an invalid byte, it's going to cause the password check to take 2 cycles longer, the length of time needed to execute the BIS instruction. Because as you look at this, there are 2 different paths through the code. We could take the jump 0 and go directly to the decrement R7, or we could not do the jump 0, execute the bit set, and then go to the decrement R7. And that 2 clock cycles is enough to be useful to us. This exposes an attack where we can measure how many cycles the password comparison takes if we have a password of all zeros. So we do all zeros, we see how long that check takes. Then we do it again with all ones. See how long it took. Do it again with all 2s. See it again with all 3s. And what this will do will give us an exact count or an exact measurement for how long all of these take, and we can see essentially a password alphabet. We will know which bytes occur and how many times they occur because we've done these different tests and timed them with alphabets of 0 through FF. So we can then use some logic to inform probable patterns. Like we said, the password is pointers, which means they all probably have similar or identical high bytes in their addresses. Additionally, on the MSP430, the addresses are 2-byte aligned. So if you have an odd byte in your alphabet, you know that that can't be one of the least significant bytes in those pointers. This allows us to then intelligently brute force the password, combine that with the increased baud rate speed, and it actually becomes a feasible thing to do and a way to extract the protected memory contents in the MSP v430 by the bootstrap loader. What about mitigations? We really need a new one for this, and this is an important one, especially with even modern CPUs. As we look at the different things that have happened with side channels, Spectre, Meltdown, this bootstrap loader look, we need to understand the concept of constant time execution. That is to say that whenever you have code that's going to operate on secret data, it has to execute in constant time regardless of the value of that secret data it's operating on. And so as you look at this, a way we can fix this in the MSP430 is to just add additional NOPs in the negative code path so that regardless of whether we take the branch that sets the bit in R11 or whether we don't, each of those code paths takes an exact same amount of time down to the clock cycle. And this type of constant time programming is important anytime you're doing any sort of operation on cryptographic data, because if the timing or power or other observable side effect of how your controller operates on that data will expose information to attackers to potentially leverage and be able to recover that secret data. And this introduced a cat and mouse game. So as you look at a mitigation, we can say, well, let's just disable the BSL. Let's make that an option. And so we'll just disable the BSL. And we have this watchdog timer anyways that's going to reset the microcontroller. So when the BSL is disabled, we're just going to do a spin loop until the watchdog timer decides, hey, you need to be reset. And that sounds great, except then now you have a great glitching target that's just constantly checking and then jumping and then checking and jumping. And now you have a ton of targets to try to glitch that jump and fall through and bypass that issue and drop back into the bootloader, into the bootstrap loader. So that doesn't work. So they can go to the other extreme, which is if you insert an incorrect BSL password even once, we're just going to do a self-destruct. So hope you don't fat finger it, hope you don't get it wrong, because even one wrong attempt is going to wipe the entire chip. So this doesn't make the BSL a feasible target. Instead, we want to look at trying to re-enable the permanently disabled JTAG. Remember, JTAG is a really common peripheral here. And so what if we can re-enable the hardware debugging available via JTAG and just ignore the BSL altogether? And we're going to get back into some new photovoltaic effects here. If we decap the chip and get it down to the correct layer, you can take a camera flash, like an old school, remember this from the 90s, right? So take a wind-up camera and flash that camera to the exposed fuses during the check. It can induce a photovoltaic effect that actually will cause it to skip that JTAG check and actually enable hardware debugging. And this was dubbed very appropriately the paparazzi attack. Additionally, there are other attacks and other microcontrollers that may or may not apply to the MSP430, but some of these configuration bits can be reset using ultraviolet light. And so if you can decap a chip down to the fuses and then apply ultraviolet light, you can use that to set bits that were previously cleared. Now, as I said, there's over 570 variations of the MSP430, and there's also different versions of the BSL firmware. So your mileage may vary, and this cat and mouse game has gone on for long enough that the exact details will be very dependent on which MSP430 variant you have and the firmware version of the BSL. And now we're going to look at the PIC18. So this is a case study because what I want to do is actually dive a little bit deeper into the data sheet. And as we look at this, this is a little bit in the middle of our timeline where it was made by Microchip, ballpark 2002, and it is an 8-bit architecture with just 77 instructions. It's got separate program and data memory and a variety of different peripherals that are very useful. And the applications for this include home alarm systems, RFID smart card readers. I've also seen it in automotives and supposedly smart medical devices and telecom. So a variety of applications there, and we're going to, like I said, start looking at the data sheet and see if we can find any inconsistencies or logical issues with this attack or with this microcontroller. So as we look here, we see that there are different banks of memory for the code memory or the program memory and the data EEPROM. And as always, we're going to be looking specifically at the F452. So this is a shared data sheet across a few different families, but we'll be looking at the F452 as a specific example. It also has a USART peripheral. If you're familiar with the UART, USART is basically interchangeable. It can be configured to be synchronous or asynchronous, and that is part of the configuration bits. Additionally, you'll notice that there is programmable code protection. That is what we're interested in looking at. And as we look at the memory map here, we can see that the memory and the program memory is broken up into different blocks. We have a boot block, and then block 0, block 1, block 2, block 3. Each of those blocks has code protection that's controlled by a few different bits. And each one of those flags will end with B for the boot block, or 0, 1, 2, 3, depending on which block we are looking at. And each of those can be individually configured. If we look at an example of a real-world target, we can extract the configuration bits using a vendor-provided tool, the PIC3. And we can see here, according to the highlighted blocks, that the boot block is not code protected, but blocks 0 through 3 are code protected. Additionally, there are some comments there about it not being protected from table reads executed in other blocks. So as we look at the code protection bits, we have to understand what these really mean. Code protection inhibits external reads and writes. What we mean by that is that there are the external ICSP pins. ICSP is the in-circuit serial programmer. That is Microchip's vendor-specific protocol for how they program their chips. And so this protocol is how we program the device, how you can read and write the contents of memory, various things. And so code protection will prevent being able to extract memory using that tool. Write protection is a way to prevent a block of user memory from being overwritten using table writes. And table writes are the other side of the coin from table reads. And a table read instruction that executes from a location outside of that block is not allowed to read from another block. So we have to really understand what a table read is here. Essentially, you can think of it like pointers. The user memory can be read or written from any location using the table read and table write instructions. So what we can do is load up the address or the pointer in a special register called table pointer, TBLPTR, and that table pointer points to each byte in program memory, in code memory. And we can use that along with the table read instruction to extract a single byte from memory. Table write is the same way, but you can also write data using the table latch tablat special function register. So can we just turn it off? So we've looked at code configuration bits as being a configurable option. So can we just overwrite the configuration bits to disable it? And no, because in order to do that, you have to execute a full chip erase or block erase function. And you can only initiate that by an external programmer using the ICSP protocol. Basically, bottom line is that we're not able to disable code protection without losing the data that we're trying to extract. Of course, except maybe with glitching, that we've seen we can do a lot of things with glitching here today. But we want to look at a few different things here and see if we can find a logic issue. When we look at the boot block, there aren't very many references to it in the data sheet, but we can find one of the things there is the reset vector. As the name implies, the reset vector contains the first bytes that the PIC18 will start executing when it is reset. And additionally, when you extract code, having these interrupt vector tables or these interrupt vector addresses is a good way to help you find your footing when you actually do successfully extract the firmware. But to do that, we need to be able to figure that out. So we're going to see here, we saw over here that it mentions a full chip erase or block erase function. And if we pull out a separate data sheet, there is a programming specification guide. And it mentions that you can do a full chip erase, or you can just erase the data EEPROM, or you could individually erase the boot block or panels 1 through 4. And we assume panels 1 through 4 are the same thing as blocks 0 through 3, because technical writing is hard. It's hard enough to get things correct within one document, let alone across multiple documents for the same chip. This introduces us to something called the Heart of Darkness attack. What we can do is erase the boot block. Remember that we already extracted the boot block. We have its original contents. We have it saved off. Now we can erase that boot block and put our own code there. We put our own code that uses the table read instruction to be able to read a program memory byte in another block, like block 0. And this works because that EBTR, external block table read configuration bit, was disabled. So we can then take that byte that we just read and we can dump it out on some GPIO pins. Now we could write our own protocol, our own way to do that, but the easiest way is to use the built-in UART peripheral. And just spit it out over the UART pins. And you can repeat that and increment and crawl through memory, dumping 1 byte at a time over the UART pins. Now, we can look at a second way of doing this too. What if our boot block was also code protected? Well, on a second device, you could leave the boot block intact and replace blocks 0 and 3 with a NOP sled that ends in the dumper code, and then use that to dump out the boot block. And then you can recombine the output of both of those devices to reconstruct all the original memory contents. And this is, again, where a picture will make sense. Now, credit goes out to the people who wrote the original Heart of Darkness paper many years ago. But on the diagram on the left is the scenario we have where we erase the boot block, put our dumper there, and are able to extract the contents of block 0 through block 3 over the UART. And then if we had a second device, we could leave the boot block intact. At some point, the boot block is going to end up jumping into somewhere in block 0, 1, 2, or 3. And we fill it full of NOPs so that when that eventually happens during normal execution of the boot block, it ends up in our dumper, which now will dump the boot block section of code. And using that, we can reconstruct and stitch together the original full contents of the chip. And then we can flash both of our devices back to their initial state. So as a generalization, if your device, if your target device allows flash protection to be configured for different blocks individually, and you can reprogram them individually, and if you can have some way for code in one block to read program memory from a different block, then it's a great candidate for the Heart of Darkness attack. So parting thoughts. There's a lot here. I told you we were going to go fast, and like I said, it's okay if you don't understand it all, but this is just a small selection of resources for specific models. There's bypassing protection on many different other microcontrollers, including from NXP, an STM32, various different methodologies and targets. And there's been some recent really good conference talks within the last couple of months If you look at hacking the Xbox One, it took 10 years or so to bypass and hack the original Xbox One, and tremendous credit to Marcus Gasadellin. And that was presented at Reverse. You can find that on YouTube from March this year, as well as Joe Brand, an excellent recognizable name in the hardware security and hacking spaces. And he has been helping people recover the contents of locked crypto wallets, doing glitching, EMF fault injection, and various things with Trezor wallets. And pretty much anything you can want, you can find resources on there. So what we need to see here is we've looked at code protection and secure boot and seen approaches that use obscurity as well as transparency. And we all know that you shouldn't be using security through obscurity, but there's nothing wrong with security with obscurity. To say, but an attacker would need to have access to our firmware in order to find that vulnerability is no longer a defensible position to take. Mitigations and configurations may make it more difficult to access those memory contents, and that's good, but not necessarily sufficient for security. And it really should be part of a balanced diet for your healthy security development lifecycle. As I said, I really want to give a credit to these resources, most of which I've gone through today, and some which I didn't even really have time to touch on, but these are a lot of the original researchers and the awesome things that they've done. Additionally, Assembly Tech Security has a workshop version where we go through a Heart of Darkness attack. And I actually was just in B-Sides giving a 4-hour workshop, and I also have a 2-day version of the training that we offer as well. And actually going through and executing this attack on hardware with hardware kits, banging protocols. You can find information about that on Assembly Tech's website. And of course, thank you so much for joining us and for learning when code protection doesn't protect code. Well, hopefully you made it this far to the end of the video. If you did, please leave a comment and let me know. While you're down there, please help us forum and tell us what you want to see out of Assembly Tech Security training. We're looking to expand our training options, and I want to tailor our next training opportunity to something that you're most interested in. Please follow us on LinkedIn. It's where most of the announcements are going to be made. I do want to make more on this YouTube channel. We will see where this goes. And if you're interested in microcontroller security, hardware hacking, software exploitation, reverse engineering, please let me know. And again, we're here to help you build your cybersecurity future, but there is some assembly required.